Hello, everyone. My name is Nathan Peck, and I'm a developer advocate for AWS Working Container Services. Today, I'm going to present this webinar, which is about how you can get started with deploying a containerized web application using the AWS Cloud Development Kit. So let me show the agenda first so everyone understands what we're going to be getting into today. First, I'm going to start out with an introduction to infrastructure as code. And the goal is, by the end of this webinar, you should be able to answer questions such as, what is infrastructure as code and why would you want to use it? Where does AWS Cloud Development Kit fit into the infrastructure as code space? And what does AWS CDK offer that's unique among other infrastructure as code providers and solutions? So once you understand infrastructure as code, the next level is, how can you use AWS CDK with your containers? And so we're going to be going into the tooling that AWS CDK offers for your containerized applications, both higher level reusable patterns and underlying core constructs if you really want to get into the low level configuration and tweak every aspect. And then finally, I'm going to show a demo of using AWS CDK to deploy a containerized application. So the goal here is to sort of build onto the concepts and bring everybody up to level on infrastructure as code, then what AWS CDK offers for containerized applications, and then finally we're going to actually dive into that code editor and be looking at some code, and I'll walk you through the process of deploying it. So starting off, introduction to infrastructure as code. The first level of infrastructure as code for many people is creating infrastructure by hand. This is a pretty common pattern. You have different developers who are all working within a shared AWS account, and they're using the console to create and edit different resources directly in the console, and the end result is that you're building out your organization's infrastructure. Now, there's a few pros and cons to this approach, and I'm not going to say that this is a terrible approach, because this is how a lot of people start out with their infrastructure as code. In particular, the pros of this approach is that it's fantastic for standing up your first project infrastructure, particularly if you're playing around with a new service that you've never used before, or you aren't quite sure what you want to build or what settings you want to use. Using the console to manually change all these settings can be very helpful. And because you're working right there in the console and have that tight interaction back and forth with the different components and buttons and fields there, you're able to see your errors faster and iterate on your settings and try different things out. But there's some major cons to this approach. If you are clicking things in the console, entering all these values by hand, that's slow. There's a limit to how fast I can click on another field and enter something on a web form. Long term, if I have a significant amount of cloud infrastructure to manage, and I need to update settings or to create new things, if I'm doing this all by hand, it's going to be a major bottleneck to my development speed and how fast I can build an infrastructure. And humans are fallible. It's hard to reliably reproduce my results if I'm doing things by hand. One day I might enter a particular value into one field, and then the next day I forgot what value I entered last time. I enter a different value. So I could make mistakes. I could forget to hit a checkbox somewhere, and that results in unreliable results from trying to reproduce things by hand. And one of the other very important issues, and this happens a lot, I see a lot in organizations that are still doing things by hand in the console, is that one person has their own idea about how they want to do things, and another person, person B, has their idea about how they want settings to be, and they end up conflicting with each other because they're both just using the console, and person A changes this setting, and then person B changes it to a different setting. And you end up with no single source of truth about how the settings and how the infrastructure should be configured in order to get reliable results always. So this leads a lot of organizations to move on to the next level of infrastructure as code, which is imperative infrastructure as code. Now, you may have heard the terms imperative and declarative before. And I'll go into a little bit about what these mean. But for now, when I say imperative infrastructure as code, what I mean by that is you have multiple developers which are working together on a deployment script. It could be written in any language. It could be a Bash script. It could be JavaScript. It could be Python. whatever language they're developing in. They're writing a script which uses the AWS SDK to talk via the AWS API and create organizations infrastructure. Now, this works. It's definitely better than doing things by hand. Here's what that ends up looking like. I have my deploy script, and it has a lot of logic in it. This is basically pseudocode, where what I would need to do is check to see if a resource exists on my account. So I get the resource, and then if the resource matches what I want it to be like, okay, we're fine. If the resource doesn't exist at all, I need to create it. If it exists but it doesn't match, then I need to update that resource. So the problem here with this approach, I put some bullet points over there on the slide. You can see lots of boilerplate. I need to write this pattern over and over again. I have to handle all the edge cases. Like, for example, what happens if creating the resource or updating the resource fails? I need to retry it. What happens if multiple people in my organization run the script at the same time and the results conflict with each other? They both try to get the resource and see that it's missing, and then they both try to create the resource at the same time. So that's called a race condition. You can end up with unreliable results because there's conflicts between person A trying to update the resource to this setting and person B trying to update the resource to a different setting. So to summarize the pros and cons of this approach, the pros are, if I write this deployment script well, it will be repeatable, it will be reusable, and I will be able to have multiple people working and contributing to this script to create infrastructure. I won't have an issue where person A is changing a setting in the console and person B is overwriting that. But on the downside, I have to write a lot of boilerplate code. It can be hard to make that code reliable, and because I have to handle all those edge cases and race conditions between different people running the scripts at the same time. So we can move on from this level 1 to level 2, which is declarative infrastructure as code. And so in declarative infrastructure as code, what we have is, instead of a script for creating the infrastructure directly with the AWS SDK, we have a document which describes the infrastructure we would like to create. And we hand that document off to a declarative infrastructure as code provider, such as AWS CloudFormation or HashiCorp Terraform. And that piece of software will then use the AWS SDK on our behalf to create infrastructure according to the description in our infrastructure document. And the end result is, once again, we're creating the organization's infrastructure. So here's what that looks like. I'm showing an AWS CloudFormation example. In this case, it's written in YAML format. So this would be infrastructure.yaml. And you can see that I have a list of resources in this document. And I see that there's a VPC resource, there's subnet resources, and each of these resources has properties. And you can also see that there's a few helper functions that are built into the YAML in this case, like find and map, or function get AZs, or function select. So this is sort of a quasi programming language. It's technically just metadata, it's structured metadata, but there are some functions built in that aid me in fetching values. But fundamentally what this is I'm not writing a code that runs logic. What I am doing is I'm describing what I would like to create. And then all the logic runs within CloudFormation. And so here's how that works. Let's say that I start out with this CloudFormation document, which describes an S3 bucket. And there's just one bucket, which I'm calling bucket 1. And I pass that off to CloudFormation. CloudFormation will use the AWS SDK on my behalf, and it will create a bucket inside Amazon S3. Now, if I add a bucket 2 to the document, here's what happens. AWS CloudFormation will go through and create bucket 2 on my behalf because I added that to the document. But if I remove that from the infrastructure as code document and repass it off to AWS CloudFormation again, CloudFormation will once again actually remove that bucket 2 according to the fact that I removed it from the list of resources. So I'm able to add or remove resources automatically from my account just by adding and removing them from the list of resources in this document. So to summarize the pros and cons of this approach, one of the pros is I don't have to write a lot of imperative boilerplate. I don't have to write code which says, check to see if this thing exists, check to see if it matches, and then check to see if I need to update it. All those resources are created, they're updated automatically by CloudFormation, just based on the fact that CloudFormation itself checks and see those differences between the document that I wrote and the real state of my AWS account. Another pro is multiple people can work on this template collaboratively. I can add some lines and some resources to the account. Someone else can add some resources to the account by adding them to that file, and we can git merge our changes together. And as you know, git merge will merge our lines together, and all the resources will end up in that same file. So conflict resolution works really well with this type of approach because the conflicts on editing the file can be resolved at git merge time. And CloudFormation itself locks resources centrally, so that way if multiple people are trying to update the stack according to the infrastructure as code file, only one of them can be updating and changing a particular resource at a time. So this works really well when you have a much larger team and you have multiple people trying to work on that AWS infrastructure. Now, cons of this approach. As you saw, there was a one-to-one relationship between resources in the file and resources that I create on my account. If I want to create an S3 bucket, I add an S3 bucket resource to the file, and then CloudFormation creates an S3 bucket resource on my account. So one of the things that this means is that there's a lot of boilerplate inside a CloudFormation file because I have to write a new resource for every single thing that I want to create. And as we saw, there were a few built-in functions in the CloudFormation YAML, but I still have limited ability to run my own logic. I can use the built-in functions that are built into JSON YAML or HCL, which is the Terraform file format, but I can't really extend it that much because I don't have a lot of control over the infrastructure as code side of things. CloudFormation is running off on the AWS side as a service. Terraform, unless I go in there and open a PR and modify Terraform itself, I can't really add new logic to my infrastructure as code. And most importantly, these file formats for infrastructure as code, it's hard to keep things dry. You may have heard this term dry. It stands for do not repeat yourself. The idea is try to avoid repeating structures over and over again in a file. Ideally, your infrastructure as code will be able to take advantage of things like loops, functions that you could call repeatedly, so you don't have to write things over and over again in your files. It's not really possible to do this with just a YAML or JSON file or HCL. So this is where we get into level 3, AWS Cloud Development Kit, the subject of this particular webinar. So with Cloud Development Kit, what developers do is they write a Cloud Development Kit application, which runs inside the AWS Cloud Development Kit software. And the end result is that it generates an AWS CloudFormation infrastructure as code template. And then AWS CloudFormation uses that template to call the SDK on your behalf and create your infrastructure. Here's how that works. I could write my application, my CDK application, in a variety of different languages. For example, JavaScript, Python, .NET, or Java. In this case, you'll see a lot of examples. I'm showing TypeScript because that's one of the languages that I favor. So you can see what that particular code looks like. Here's a snippet. It looks like your standard JavaScript, TypeScript application with a class and constructor and different class instantiations in there. So I'm able to write in a familiar programming language. I'm able to create multiple AWS resources at once, and I'm able to organize those resources into different stacks, all within the same application. And this is still declarative. I don't have to write logic to check to see if there's a VPC. All I do is say new EC2 VPC, and the VPC will be created if it does not exist, or it'll be updated if it does exist. So I want to zoom in on one of the points from the last slide, which is that a construct inside CDK can expand to many underlying resources. So let's take this line, for example, where I'm saying VPC equals new EC2 VPC. And I'm passing in some options to the VPC instantiation, saying that I want the max AZs or availability zones to equal 2. So if I take this line and I use the CDK deploy command built into CDK, here's what will happen on my account. You see a list of resources that are being created down there on the bottom. I'm not only creating a VPC resource, but I'm also creating an internet gateway, a NAT gateway, actually 2 NAT gateways for high availability. I'm creating a total of 4 public or 4 subnets, 2 public and 2 private. And so you're seeing a variety of different resources that are all created with just one line. And to summarize just how much configuration and resources are being created via this one command, let's compare how that would look if I was running CloudFormation. If I was running CloudFormation, it would actually be over 270 lines of CloudFormation to describe all of those resources, the different subnets, not only the subnets, but also the routing tables and configuration that connect those subnets to the internet gateways, to the NAT gateways, and place them within that VPC so that way they can be used. So as you can see, this one command is very powerful because I could also change that max AZs to 3 and it would automatically create 3 AZs. I'm able to have all this power to configure something that is very hard, very verbose to configure, but configure it with just a few commands and a few changes to my configuration. So I want to move on from this to the next major benefit of CDK, which is how it can help you with your local workflow as well. So we discussed how infrastructure as code passes off and calls the AWS SDK on your behalf. Well, with CDK, another thing that it can do is actually run commands and operations locally on your developer laptop or on your CI/CD build machine on your behalf in order to prepare things for their journey and deployment to the cloud. So in this case, we already talked earlier about creating an S3 bucket via infrastructure as code. So here you can see how you would do that with CDK. I would just say new S3 bucket. And here, what I'm actually doing is with just a couple of commands, I'm specifying that I want this to be hosted publicly on the internet, fetching the index.html file, and I want it to be publicly read. And it's going to go out and automatically sub this S3 bucket as a website for me. But one of the things that I need to do is I need to get my files into this bucket because if my files aren't there, then all my visitors are going to see is a 404, website not found error. So one of the things I can do with CDK is create a bucket deployment resource. And what this allows me to do is take a local folder on my developer machine, zip it up, upload it to AWS, and then on the AWS side, a Lambda function will run to go ahead and automatically unzip that folder into my S3 bucket for me. So it's very fast, very efficient, and it takes care of this automatically. Normally, I would have had to create that S3 bucket by hand or by infrastructure as code. And then as a follow-up, I would have to write my own script or manually do a process of uploading those files off my laptop and into the S3 bucket. CDK helps me with that workflow by automating that part as well with just a few lines of code. That means I don't have to write as much scripts. I don't have to do as much manual work because it's being done for me automatically. Now, another major benefit of CDK is that the different constructs that are being provided, all the constructs that I've shown so far, and all the ones that we will talk about, are shareable and reusable. And what I mean by that is there are different people from different companies all collaborating together to create these constructs. So, for example, that construct for VPC that I showed earlier, that construct that expands out to 270 lines, it was designed by a combination of AWS engineers within AWS and with input from various customers and different companies that need to use VPCs on their AWS account. So as you can see, everybody is contributing together to create this construct for what a VPC is and how to configure it. So that includes the expertise of, for example, the engineers that actually created the VPC concept within AWS. They have particular guidance on how to configure a well-crafted VPC, and so their input goes into creating this construct. If there's a bug fix, perhaps that was contributed by one of our customers, or a customer says, this construct is a little bit hard to use. I really wish that I could easily go from 2 AZs to 3 AZs in my VPC. Well, they can contribute a usability improvement to it. So one of the ideas that I want you to understand about CDK is that when you use CDK and when you use a CDK construct, you are essentially standing on the shoulders of giants because you're able to utilize the expertise and shared skill of all the people who have contributed to that construct. And we also encourage you, if you run into something that you would like to see from CDK, you can also contribute your own features, usability fixes, or even just open an issue on our GitHub asking someone else to fix it for you if you're not quite certain whether you can yourself. And so just to give you an idea, here's a list of the different open source constructs on NPM. I had to truncate this list because it was actually so long. I was only able to go from A to I. So there's still, I to Z different lists of constructs that are available to you. Some of these are managed by AWS. Some of them are actually contributed to and created entirely by third parties as an abstraction layer on top of these core constructs. But you can find the open source code for all of these different things and play around with them yourself on NPM with just a simple search. So to summarize AWS CDK, going into the pros, obviously CDK is still declarative. I don't have to write boilerplate to handle whether I'm creating a resource, updating it, deleting it. The declarative code that I write is made up of higher level constructs that automatically create many underlying resources. So I don't have to go through and handwrite one by one all the different bits that I want to create and hook together. In many cases, I can say, I would like to create this overall thing. I would like to create a VPC that's high availability across 2 AZs. And CDK understands how to take that high level ask and turn it into all the low level components that are required to make that function. Multiple people can work on a CDK app collaboratively. Not only can they share their constructs with each other, but they can also, once again, they can work together on that app and deploy it simultaneously because the race conditions are handled and CloudFormation will handle whether or not 2 people are trying to update a stack at once. Conflict resolution is easy. Git merge will merge CDK code together quite nicely. I'm also able to use familiar programming languages. So whereas with CloudFormation or many other languages, I have to learn either a new, I need to learn a new way of describing my infrastructure, or I have to write in YAML or JSON. With CDK, I'm able to write using the same programming language in many cases that I would write my own application in. So Python, JavaScript, TypeScript, .NET, and Java. So this is a huge benefit because it really opens up the ability for your application developers to also contribute to infrastructure. I don't have to have an infrastructure guru who knows how to write CloudFormation YAML or knows how to write a specialized file format to describe my architecture. Instead, my engineers can use the same language that they're already familiar with and the same documentation format to understand that SDK for CDK and start creating infrastructure. Additionally, CDK does more than just create cloud resources on my AWS account. It also helps in my local development workflow. We looked at an example of how to zip up and publish a folder to an S3 bucket. And we'll look at some more examples of what you can do with that once we get into containers. And then finally, one of the things I want you to understand about CDK is that you can easily share and reuse constructs. They're all open source. They're all on NPM. And when you do that, you're benefiting from the best practices in these constructs designed by experts who are very, very familiar with these tools and these AWS resources. So hopefully by now I've sold you on infrastructure as code and why you would want to use AWS CDK. Let's get into how you would use AWS CDK with a containerized application. And first, I just want to go into some basic container concepts to make sure everybody is on the same page. So with the container, obviously, when you're developing an application, everything starts with a folder full of code on your local computer. This is where you're actually writing the application and running it. Now your goal is to actually run this application in the cloud or on a server somewhere. So Docker build is a command that you use to take the code files and take all the dependencies of your application. Let's say it is a JavaScript application and you need to have the Node.js runtime, or it's a Python application, you need the Python runtime, or maybe you need to compile a executable. Let's say it's a Go program, you need to actually compile the binary for that program. Docker build is the step where you take all that code on your local machine and package it up into one thing that can actually run and actually has all the resources that your application requires in order to run. And then the next level is Docker run. This is where you take the container image that you built and you actually create a running copy of the application based on this image that you had previously built. So working with a container is this process of taking the local things off my computer, packaging them up into a Docker container, shipping that container to the cloud, and then Docker running it there. And in order to help with that, AWS has solutions for container orchestration. So I'm going to talk about AWS Elastic Container Service, because this is the native solution for container orchestration that we've built that's designed to be closest to the AWS resources and closest to how we operate internally within AWS. So in order to launch a containerized application on AWS with ECS, the first step is registering a task definition. And the idea behind a task definition is it's just a description of what application you're running and what settings it needs in order to run. So for example, it would point to the Docker container that you want to run. And it would say, for example, this container requires 2 CPUs and it requires 2 gigabytes of memory in order to run. And once we have all that description of how to run, we'll be able to use that later when it comes time to actually run that application. The next concept behind container orchestration is the idea of creating a cluster. And the cluster is just capacity that you would run your application on. And you have 2 options there. You can either establish EC2 instances, which provide the capacity for running your application, or you can stay serverless by using AWS Fargate as your cluster. And with that, Fargate will provide essentially an infinite capacity cluster to you that allows you to run as many containers as you need without needing to keep track of a pool of EC2 instances. So the next level in container orchestration is the idea of running a task. Now, running a task allows you to launch a standalone task into one of your clusters. And what it does is it uses that task definition that we previously registered as the description of what application to run and how to run it. And when I run a task, it just runs on one of the machines in my cluster or in Fargate until it completes and exits. But not every application fits that that workflow. You know, if I want to run a single standalone task, that's great for maybe crunching some numbers, generating a report, something like that. But oftentimes what I may want to do is run a web service. I want to run something that's always up and running. It's waiting for requests to come in from a website and serve back a page. So there's another tool called a service, which is a way to run multiple copies of one of those task definitions and hook them up to other resources on my AWS account, such as a load balancer. And so with this approach, I could say I would like to run 3 copies of my process distributed across my cluster for high availability. If one of them crashes, I'll still have 2 more up and running in order to serve my customers who are visiting my website. And I want to keep them running until I say to stop them. And I want to hook them up to a load balancer. And so that way, if anybody requests my website, the request will come in and it'll be distributed to one of those running copies of the task inside my cluster. So at a high level, these are the concepts that you need to understand in order to work with containers. You need a container image. You need to run the container image. You need to describe how you would like to run it, provide capacity to run it, and then you can optionally either run it as a standalone one-off or run it as a service that stays up and running at all times. So we provide 2 levels of container abstraction in CDK to help you achieve these different patterns that are necessary for running a containerized application. The first level is the AWS ECS construct, and the second is the AWS ECS patterns construct. So just to compare these two, the AWS ECS construct is just the basic patterns. This is what's going to help you build your Docker image, create your cluster, create your task definition, create that task or service that I referenced earlier. And we consider this to be a stable release. All these constructs are ready to go. They're ready for you to use. And we're very satisfied with them. Now, AWS ECS patterns, this is the next level of abstraction above AWS ECS. We do still consider the stability of this construct to be experimental, but thanks to the versioning of NPM, you can feel free to start using these today. Just keep an eye on the patterns themselves, because we may, for example, change some of the APIs or some of the names on some of the methods. So if you are upgrading from, say, version 1.7, which is in this slide, to version 1.8, which is the current version as of this webinar, that would mean that I need to modify maybe some of the code inside of the AWS ECS patterns inside of my CDK in order to use those. But the patterns that we're currently providing are a load balanced service, a service that's behind a load balancer, a queue consumer, which is a background worker service that pulls work off of a queue and processes it, and also a cron service, which allows me to schedule a task to run at a specific time or on a schedule, like every day at 5 o'clock. So once again, these patterns are still considered experimental instability. We're still actively working on these, but I want to show them anyway because I have been using them for some time and a lot of people are using them. You just need to be ready to update if we do need to make a breaking change to the API on some of these patterns. So let's dive into the basics of CDK. My goal here is to present the simple pieces of CDK for ECS that would allow you to get your first CDK program written just by copy and pasting in about 5 minutes. So the first piece, and this is one of my favorite pieces, is a tool for building a container image. So I talked earlier about how one of the benefits of CDK is that it can help you with your local workflow. Well, one of those local workflows that it can help with is building and pushing your container to the cloud. So if you've ever built a Docker container before, you're familiar with the fact that it takes what's called a Docker file, which is a description of how to grab resources and code files off of your local machine and package them up. And then there's a process called a Docker build, which generates the container image, and then you'll Docker push to push it to the cloud. Well, all of that can happen end-to-end automatically with just one line of code, which is I'm saying ECS container image from asset, and then I'm specifying the path to the folder that actually contains my Docker file in my code. And that's all I need, just one line of code, and it will automatically go out there and find the Docker file, build it, and even automatically create a EC2 container registry and push my Docker container to it. So that way it's stored on the AWS side, ready to run. Now, once I got my container image, I need capacity to run it in the cloud. And so the next construct that I want to introduce is the way to create a cluster to run your application. Now, it's pretty easy. I just have to create a VPC in order to hold the resources on my account. And I already talked about the VPC earlier, how you're getting this best practices, high availability VPC that's distributed across 2 AZs. And so that's what you see here. However, the next thing I can do is I can add a cluster into that VPC using the ECS cluster construct. And you can see that by default, all I have to do is pass in the VPC that I want it to be created in. And then I have 2 options. I can either choose to stay serverless with this cluster and only use it with Fargate capacity, or I could choose to optionally add EC2 instances to this cluster in order to run directly on EC2 instances. And if I want to add EC2 capacity, it's very easy. I just say cluster add capacity. I specify the instance type that I would like to add, and the number that I would like to add. And you can see that here I'm adding the T2 extra large instances because those are pretty nice. And I'm adding 3 of them. So I've created my cluster. I've built my image. The next thing I want to do is I actually want to run it. And so the first ECS pattern that I want to introduce here is how I would launch a load balance service. So you can see how these ECS patterns that I talked about work. So you'll see that ECS container image from asset command is once again is there in the code. But here what I'm doing with it is I'm wrapping it in another construct called load balance Fargate service. And so what I'm doing is I'm passing that cluster that I created. I'm passing in the image that I'm building, which is my app image. And then I'm also specifying how many containers I would like to run. And so just like that, with 1, 2, 3, 4, 5, 6, like 9 lines of code, I'm able to create an ECS cluster on my account inside a high availability VPC. And I'm able to launch, build my container and launch 3 copies of it, in fact, inside of a cluster. And so I'm now running in this robust high availability configuration that's distributed across AZs, and everything is ready to go. I could actually host a pretty decent website that would be high uptime. It would scale pretty well because I have multiple copies of the running container. And this is all I would need to host a single web service. Now, let me move on to another type of ECS pattern that I hinted at earlier, which is the queue consumer. This one is very cool because not every type of work that you want to do should be done in the foreground. Like, for example, if I'm loading up a website and that website is sitting there spinning in my browser for 3, 4, 5 seconds, that wouldn't be a great experience, right? I usually want my website to respond really fast. But sometimes there is a heavier piece of work that you need to do. Maybe as part of sign up, you need to send some emails, or you need to crunch some numbers, or do some kind of task, which you don't want your users to have to wait on. You can do it in the background. So with this pattern, what I'm doing is I'm creating a queue, which is basically a list of jobs that I want to do. And I'm creating a service which is hooked up to that queue. And I'm specifying a container image that I'm building, which will listen to that queue and grab work off of the queue. And so with this pattern, what it'll do is it will actually auto scale the number of workers according to how many items are on the queue. So because I specified in this code that the desired task count is 3, it will start out with 3 workers. But let's say that I had a big burst of activity on my website and people started queuing up a lot of jobs. It would actually be able to scale up the desired task count automatically as the queue backs up, and scale it back down as the queue gets cleared out. And so this provides a very easy pattern for creating a service which is hooked up to this queue and can handle any amount of traffic that I might need to throw onto that queue if I have a lot of jobs to do. And now one of my favorite patterns is the time schedule container. Typically, if I need to execute a job every day, for example, at a certain time, that can be a pretty hard pattern to solve. You know, if I was just working on one EC2 instance, there's a tool called cron that is distributed as part of a Linux machine where I could say, every day at 5 o'clock, run this job. But then what if that instance goes out of service, or somebody messes up that instance or shuts it down? Well, then my cron job wouldn't run. So one of the problems that can be a little bit hard to solve is the idea of high availability cron. And a scheduled Fargate or EC2 task is a way to get high availability cron. With this, what I'm saying is, here's a cluster, and here's an image that is my application I want to run every day at 5 o'clock. And here's a schedule expression, which is how I would like to run it. So here the schedule expression is rate 1 day. So I'm saying every day I would like to run it. But I can also specify a cron expression to say, for example, every day at the specific time, or every hour, or only on weekdays, or only on every Thursday. So I have this ability to take a arbitrary schedule and run a single task to completion inside my cluster on that schedule. So this is a very useful pattern for building in the cloud. So now I introduced these high-level patterns, let's dive a little deeper now into how I can use the AWS ECS manually to create some of these same things myself. Because sometimes you might want a little bit more control over the settings. As you saw, for example, the load balance service, there weren't a whole lot of settings on that construct. It basically hooks up to that load balancer automatically. But what if I want to really dive deep in there and fine tune how things work? Well, I can still create a task definition and service manually as well using the AWS ECS construct. So here's how I would do that. Here's an example of creating a task definition and adding my container that I'm building manually. And here you can see that I'm specifying a memory limit. I'm manually controlling the ports to hook a particular port 80 up to port 8080 on my host. And I'm creating a service using that task definition. So you can see that if I want to, I can dive a little bit deeper. I can skip using the load balance service, and I can instead choose to modify the underlying settings directly by creating those resources manually. And that also holds true for the load balancer itself. So here you can see that I'm also choosing to create my own load balancer with my own specific settings. And I'm also choosing to attach my service to the load balancer manually as well with my own custom health check settings. So this is nice because I have two options. I can either go the easy route and let CDK choose for me how to create a load balanced application, or I can choose to create these resources myself. But at the same time, it's much easier to use CDK to create these resources because it has some of these helper methods like add targets. If you're familiar with creating an application load balancer, you have to create a target group by default. You have to do a little bit of plumbing to get security groups right, so that way the load balancer can talk to the service. Well, with CDK, I don't have to do that. All I have to do is create the service and the load balancer. And when I say add targets, it's going to automatically create the target group. It's going to automatically adjust the security groups to ensure that the load balancer is able to talk to my service. So this removes a lot of responsibility that I would normally have to do manually in order to make these things work. And this also holds true for IAM roles. If you are an experienced AWS user, you're probably familiar with the concept of creating an IAM role which authorizes an application to use other resources on your account. For example, in this case, I have an application that I want to be able to read and write data from a DynamoDB table. And I would also like it to be able to publish to an SNS topic, maybe in order to send a push notification or an email or something like that. So with CDK, I can use these smart helper methods, which are built into the different constructs in order to easily grant access without needing to write an IAM policy by hand. So here you can say, I'm using a helper method on the DynamoDB table construct, saying my DynamoDB table grant read-write data, and I'm granting it. What am I granting it to? I'm granting it to the task role for my particular application. And the same thing for a topic. I'm saying topic that grant publish. And so behind the scenes, what it's doing is it's automatically creating the IAM roles, and it's automatically adding to those roles a minimal set of permissions that allow my application to do exactly what it needs to do, but nothing more. So this helps me to be more secure, and it helps me by saving time from having to write these policies and create these rules by hand. So let me summarize a list of things that AWS CDK can automate away for you. Security group, so it'll automatically create security groups and minimal security group rules that allow your load balancer to talk to your containers. It can automatically create IAM roles for your tasks and automatically add minimal access to other resources. It can automatically build your container image and automatically push it to an automatically created ECR registry. And it can even automatically create a load balancer and target groups and attach that load balancer to your service if you're using that AWS ECS patterns for creating a load balance service. So let me show a quick comparison of two different approaches to using containers with CDK. On the left-hand side, you see the ECS patterns approach, which is that higher level construct for a load balance Fargate service. And as you can see, it's really only 5 lines there to start building my image, deploying it hosted behind a load balancer. And then over there on the right-hand side, you can see a slightly more verbose but more customizable approach using the lower level AWS ECS constructs. And in that approach, I have to actually create the EC2 task definition, I have to create the service, I have to create the load balancer, and I have to add the service as a target inside of the load balancer. Now, if you're just getting started with containers, I would recommend sticking to the left-hand side, stick to those ECS patterns, because it's going to automate away a lot more of the complexity for you. But if you are an experienced user, I would say use the pattern on the right-hand side if you would like to customize more of the settings to match what you would like to do. And in order to do that, you do need to be somewhat familiar, with the different pieces that are being built. But either way, no matter which pattern you use, these patterns are much less verbose and they handle a lot of the complexity for you automatically. And so let me show you these in action. I've showed a lot of static code on the slides. It's time to actually look at some of this code in action on my code editor. So I've pre-prepared some code for a CDK application, and you can see the pattern that I'm using inside the CDK application is the slightly more verbose pattern. I'm not using the ECS patterns here. I'm using the actual ECS constructs themselves directly. Like I said, if you are a more experienced ECS user, you may choose to do this as well because you want to be able to customize all the settings. In this case, I am, fairly experienced ECS user, so I do have some settings that I really want to be able to customize, like the percentage of tasks when I'm rolling things out. I really want to be able to customize some of these health checks and deregistration delay on the load balancer. And so I've chosen to use the lower level constructs for ECS and create my own load balancer, create my own target group, and manually add my own service to my load balancer instead of using the load balance Fargate task definition. As you can see, it's still, though, only 84 lines here in this code, 84 lines to get to the end of this application. So this is not a whole lot to write, and I could even simplify this some more myself by actually taking these lines here and probably packaging them up into my own reusable class that I could then share with other people as well as a Nathan Peck load balance service, which is a load balance service that has my particular settings that I would tend to favor. So as you can see, this is very reusable. It's very shareable, what I'm doing here. So let me show the application that I'm going to be deploying today. Pretty simple application. All it's doing is a hello world, and it's responding with the IP address of the particular container and hello world. So let me show you how working with CDK works. I'm inside my application folder, and I'm going to run a script to synthesize a CloudFormation template for my application. And when I run it, this command I'm running is actually piping it out to a file, synth.yaml. So let me look at that file now, and we'll see what CDK generated. And you can see that it took all of this TypeScript that I wrote, the 84 lines, with all these constructs, and it generated a YAML file, which is, let's go down to the bottom and see. It is 700 lines long, so that's a pretty big expansion, and a lot of that is a testament to how much of the settings CDK automates away for me and does automatically. All the things like creating that ECR registry, building that image automatically and pushing it up, creating those roles automatically and the different rules, CDK is saving me a lot of time and a lot of effort to create and type all of these lines, or even just copy and paste them from somewhere. So let me actually deploy this now. I'm going to run script deploy. And because I have already deployed this before in the past, and I actually haven't changed my application, what you're going to see is that this deploy goes through fairly quickly, because all it's doing is checking. It sees that actually nothing changed. Here you see this output that says no changes. And I see an output, which is the URL of my application. So if I take this application and I load it up inside of my browser, I can see a hello world response here in the browser. So my application is already running. What I would like to do is I would like to ship an update to this application. So what I'm going to do is I'm going to go into my application. I'm going to say hello webinar attendees instead of hello world. And when I change this, all I have to do is go back to my terminal and rerun that deploy script again. And you're going to see what it does this time around. So the first step is it compiles my TypeScript into JavaScript and starts running it. And the next step is it starts building and rebuilding my application. So I mentioned earlier about how CDK helps with your local workflow. Well, that includes automatically sending my build context to the Docker daemon and building my application for me, as well as already pushing the application to the cloud. And so as you can see, this is very fast, it's very efficient, because most of the layers already exist. It only has to push a very small diff up to the cloud in order to push my application. So the next step is it's going to hand off control over to CloudFormation to create a CloudFormation change set and start deploying the application. And you can see that even while I was talking, that's what just started to happen. It created a new task definition, which is very fast. All it's doing, as I mentioned earlier, the task definition is just that metadata description of what application I want to run. So it's very, very quick to create that task definition. And the next step, though, is to actually ask ECS to update my service with this new version of the application. And this generally takes, with the settings that I specified in my TypeScript, about 2 minutes. So I'm not going to make us sit here and wait on this terminal while this operates. Instead, I'll go ahead and show you in the AWS console what the ECS is doing and what CloudFormation is doing. So if I go over here to the CloudFormation service, you'll be able to see that I have a stack that's currently update in progress. And if I go in here and I look at the template itself, you're going to see the very same thing that I synthesized locally has been uploaded to CloudFormation for deployment, that very same file. So this is useful because I can run that synth command locally just to verify that things are going to work. And then I can type CDK deploy, and it will go ahead and redo that synth and upload it to CloudFormation in order to work. And you can see that CloudFormation is keeping track of all the resources on my account. This is a little bit hard to read because I zoomed in so far. Yeah, you'll be able to see the different resources that are in progress on the account. And if I go over to Amazon ECS, you can see that I have my service here. And if I click into it, I can see my tasks, which are now running. So let me go back over here to this and see how the progress is going on updating this. I can click on my service and view the events for the service as well, in order to see that all this is happening automatically from that one command. So you can see that it stops running tasks and starts running new tasks. And it says now that it's actually reached a steady state. So let me see. I refresh this. Yep. If I refresh it, I see hello webinar attendees now. So it takes about 2 minutes. This is the process by which it gradually does a rolling deploy across your cluster and validates the health of the new container to make sure it had passed. Like, if I had typed in, for example, a bug in my application code, it would be very careful about rolling that out to make sure that I didn't roll out a bad deploy and actually break my application. So at this point, hopefully you've been convinced that CDK is pretty nice. And I want to reiterate this agenda and make sure we cover all our topics. So I introduced the fact that infrastructure as code is this fantastic tool for making it much easier for you to create resources on your account without a lot of manual work. I introduced the fact that CDK is a way for you to create infrastructure as code in your own programming language that you're familiar with, and it allows you to create higher level constructs that create many low level resources on your account. It's unique in that because it has a lot of these helper methods built in that automate away a lot of the manual work that you would normally have to do. And it helps with resources locally on your account. And it's shareable. You benefit from the expertise of all the other people who are also using CDK and contributing to it. I also introduced the levels of tooling that AWS CDK offers for containerized applications, both the AWS ECS and the AWS ECS-patterns constructs for containers. And I showed both how you can use the high-level pattern or how you can go a little bit deeper into the more advanced configurations by using the lower-level AWS ECS patterns. And then finally, I showed that demo of how to use CDK to deploy that containerized application. Thanks a lot, everybody, for attending. And at this point, we're going to transition over into a Q&A where I'll be able to answer a few of your questions.